Introduction to electric EV motors. Electric EV motors are primarily two types of motors are using: permanent magnet synchronous motor and induction motor. Permanent magnet synchronous motors are attached to the rotor and alternating current supply to the stator winding. Key principle include magnetic field interaction. The interaction between the rotating magnetic field generated by the stator and stationary magnetic field of the rotor creates torque. High efficiency EMS offer high efficiency and power density due to the absence of electrical losses in rotor windings. Controlled speed and torque. Speed and torque PMS are controlled by adjusting the frequency and amplitude of AC current, typically managed by inverter. Induction motor. Induction motor, also known as the synchronous motor, another type of electric motor used EV. They operate based on the following principle: electromagnetic induction. Use electromagnetic create a rotating magnetic field in rotor. When a stator AC supply creates rotating field, it induces a current in rotor generating torque. Advanced techniques used the motor required combination of traditional advanced techniques. The goal ensured optimal performance, efficiency, and safety. Motor tester specialized equipped for testing motor performance, including voltage, current, and temperature. Insulation resistance tester measure the resistance of the motor winding to ensure there are no insulation breakdown. Voltage and current analysis monitor the voltage and current supply to the motor. Irregularities can indicate issues such as the faulty inverter, wiring problems, or issues with the battery pack. Temperature monitoring. Overheating can be sign of the internal motor issue or cooling system failure. Use temperature sensors to monitor the motor and inverter temperature. Vibration analysis. Excessive vibration can point to the mechanical issue such as misalignment or imbalance. Vibration sensor can help diagnose this problem. Acoustic analysis. Unusual noise may be indicate mechanical wear and component failure. Acoustic sensors or listening device can help pinpoint the source of noise. In this video we will discuss about how the stator windings are calibrated to each other and how it's create the voltage. Basically, if we can see, this construction is all about means the system is only connected with the inverter from the stator side, and the permanent magnet is behind it. Electromagnetic induction. Interaction as the rotating magnetic field from the stator interact with the stationary magnetic field of rotor, it produces torque. The torque causes the rotor to turn, producing mechanical power. Induced current. The rotating magnetic field of the stator induce a current in the rotor windings. PMSM. However, the rotor does not have windings. Instead, it relies on interaction of permanent magnet with stator field. The frequency and amplitude of AC voltage of stator are controlled by inverter. Only inverter is like working as a brain. This control allows to precise management of motor speed and torque. Basically, the principle of three-phase stator frequencies. The three-phase is powered by three-phase alternating current AC supply. This supply consists of three separate electrical current, each of phase with the other by 120 degree. This configuration results in rotating the magnetic field in stator of the motor. The stator frequency is the frequency of the AC power supplied to the stator winding of the motor. It determines the rate at which the rotating magnetic field is generated within a stator. The standard supply frequency normally 50-40 hertz, or depend upon the vehicle or motor condition. Normally we can analyze these frequency in our oscilloscope, so we can see how the different frequencies are operating with the different channels A and B and C. So we can see the rate of the operating voltages supplying to the inverter. Then inverter is using this voltage in charging the battery or supplying to the motor to operate the vehicle. We can analyze that when rotation of one winding it supplies AC voltage, then turn from the another winding come to the rotor, then it supply another frequency, and after one another. So it make a permanent and continuous voltage to the system who can operate the inverter converter assembly and provide the voltage to the motor assemblies. These are the points here which these connections are connected with this inverter assembly, and these wirings are the high voltage power supply. Sometimes it's giving to the voltage to the motor, and sometimes the voltage is giving back to the stator in order to charge the battery. We can say regenerative braking system in vehicle, while you have remove your accelerator pedal. Experimentally, if we see how the needle is moving while we attach with a motor assembly, so you can see if I rotating the motor assembly, it's producing the high voltage, and you can see the needle is moving negative to the positive side or positive to the negative side. It's mean that it is the voltage supply is negative to positive, like the frequency, like AC alternating current, not the direct current. And this system is only connected with this stator assembly, not the others. If you set the oscilloscope, digital oscilloscope with multiple channels, it's required to analyze three-phase signals. High quality oscilloscope probes suitable for the voltage level and frequencies. The three-phase motors or signal generators simulate the motor output. Set the basic time, capture the complete waveform cycles for these phase motor. A time base is 1 millisecond per division to 10 millisecond per division is typically used depending on the motor operating frequency. Adjust the voltage scale to accommodate the amplitude of the signal. Ensure the scale is appropriate for the expected voltage level. Use the edge targeting and select one of the phase and targetings to stabilize the display. Alternatively, use targeting a specific phase if you are troubleshooting the particular issue. Phase relation: the waveform from each three phase should be 120 degree apart. This phase shift create rotating magnetic field in the motor. Amplitude: all three waves should have similar amplitude if the motor windings are balanced and power supply is functioning correctly. Measure the phase difference between the waveform of the each phase. Each phase should be 120 degree out of the phase with the other. This can be observed as 1/3 cycle shift on oscilloscope display. The waveform should be sinusoidal. Deviation from sinusoidal shape can be indicate harmonic distortion or fault. Okay, we can see here if there is some abnormality found in the waveform, we can analyze that there is any stator abnormality is there, so we can easily catch the motor it is faulty. Fault analysis is critical for diagnosing and preventing motor failure. Some common faults are, and their analysis include: open circuit can occur due to the broken windings or connection. Insulation failure can be cause winding short circuit leading to overheat. Motor current signature analysis can be used to detect anomalies in the stator current. Can broken rotor bars can lead uneven torque, vibration, and reduce the performance. Incertainty, misaligned or imbalance can cause the mechanical vibration. Inverter failures can be due to the overheating, voltage spikes, or component degradations. Detection, monitoring voltage and current waveform, thermal imaging, and real time diagnosis. Pulse width modulations is a technique used by the inverter to control the frequency and the voltage supply to the motor. By varying the pulse width, the inverter can precisely control the effective voltage and frequency, allowing for effective motor control. Advantages: smooth speed control and acceleration, reduction of harmonic distortion, improved energy efficiency. Challenges: PWM switching can introduce electromagnetic interference and cause additional losses in motor winding. Sensorless control: many modern EV motors use sensorless control techniques where the motor speed and positions are estimated rather than measured directly with sensor. This approach reduces cost and complexity. Back EMF, electromotive force, estimate the voltage induced in the motor winding by the rotor's magnetic field is used to estimate the rotor position and speed. Flux estimation: this magnetic flux linkage is used to estimate rotor position and control frequency. Accuracy of estimation can be affected by load variation, temperature, and motor design. Field Field oriented control, FOC, also known as vector control, is a sophisticated control strategy that manages the motor magnetic field and torque production separately. By controlling the frequency of the current supply to the motor, optimize the motor performance. Benefits: high dynamics performance with precise torque and speed control, improved efficiency especially at low speed. Now I attach the resistance between one winding to another, so you can see there is a huge current passing through the resistance, and if after some time it will be burn out. Similarly, the same scenarios happening in the inverter converter assembly also. If there kind of things or resistance found in the system, it can make burn. As I told earlier that this AC motor is continuously providing the voltage in the form of wave. So the one motor comes, the one frequency, then another, and just so on. So it creates high power and voltage which causes the burning of this resistance. So so now I'm going to discuss case study with stator winding fault in PMSM. A fault occurred in the stator winding of the permanent magnet synchronized motor used in EV. The MCSA was employed to detect an unusual harmonic stator current, indicating a possible winding fault. Means the frequencies are disturbed or irregular. The solution was the motor was disassembled, and inspection confirmed the presence of insulation degradation in winding. The fault winding was replaced and the motor was reassembled with improved insulation material to prevent future occurrence. Case study 2: bearing fault in induction motor. An induction motor in an EV started exhibiting increasing vibration and noise during the operation. Vibration analysis was conducted, revealing a characteristics of the frequency associated with the bearing defect. Further inspection using thermographic imaging showed localized the heating at bearing, confirming the fault. Solution: the bearing was replaced and lubrication system was improved. The motor vibration level returned to the normal and noise was eliminated. The study case number 3. A fleet electric bus began experiencing inconsistent performance and overheating in their induction motor, particularly during heavy acceleration. The issue was traced back to the motor winding. Analysis: the symptoms reduction. The bus were brought in for inspection after multiple drivers reported reduced acceleration and increased the noise from the motor compartment. Initial diagnosis included motor current signature analysis, which revealed irregularities in stator current waves, a specific harmonic and often related with the internal turn short circuit was amplified. Further investigation, engineers was partially discharge testing to identify insulation weakness in the stator winding. The test indicated a localized breakdown in insulation, confirming in inter-turn short circuit. Thermal imaging showed hot spot in winding, reinforcing the presence of short circuit. The solution: the affected motor was disassembled and faulty wiring were replaced with high grade insulation material to withstand the operational stress. The bus were also fitted with a real-time current monitoring system to detect such fault early in future. Outcomes: after repair, the bus resumed operation without further incidents, and the early fault detection systems help prevent similar issues in other vehicles. EV manufacturer normally uses that kind of things in the motors because the motor is the most usable part in the EV vehicles, and it's the whole vehicle is depending on it. Normally, sudden losses of power, unusual vibration in some of their models, the particularly pronounced at high speed. Other testing also there, a current signature analysis was conducted, which showed the characteristics frequency of rotor faults, confirming that rotor bar breakage was the cause. The motor were disassembled, and visual inspection confirmed that the several rotor bars had indeed broken or crackage. The solution is manufacturer redesigned the rotor with reinforced bars and implemented a new manufacturing process to reduce stress during operation. Existing vehicles were recalled for the rotor replacement and installation of enhanced diagnostic software that could alert driver to potential rotor issue before they become the critical. The excessive current generates intense heat in winding due to the resistance losses. Since the current is far beyond the motor rated capacity, the windings will rapidly overheat. Insulation breakdown normally, and the overheated can cause the insulation on the winding breakdown even further, embedding the short circuit. This can lead to complete insulation failure and possibly melting of the winding materials. In extreme cases, the intense heat can be ignited and insulation material or other nearby component leading to the fire. Normally it could not be happen when the inverter converter assembly detects the short wiring. It automatically disconnect the voltage power supply to the motor, and the vehicle will not move even a single meter or single inch because of the discontinuous of the voltage. Without the proper magnetic field, the rotor might continuously spinning due to the inertia. but with no torque being produced, it is usually quick slow. If the short circuit occurs while the motor is under load, the sudden loss of torque can cause mechanical stress on the rotor and connected to the driveline component, potentially leading to the mechanical failure. If that kind of normally short happens, the excessive current can blow the inverter power transistors or cause other failures in the power electronics, which totally stop the voltage supply to the motor in order to save the motor and the any things which are related or associated with motor. Normally, when the stator windings are shorted together, the electrical impedance of the motor drastically reduces. The impedance of the motor winding includes both resistance and inductive resistance. In normal operation, this impedance limits the current flow to the safe level. However, in short circuit condition, the impedance is effectively bypassed, leading to the almost direct connection between the power source and the windings. The current flow becomes limited only when the resistance of the copper winding, which is very low, leading to the enormous surge in current, typically measured in the multiplies of the motor nominal current, often 10 to 100 times higher. The motor relies on a carefully balanced electromagnetic generated by stator windings to produce torque. With all windings shorted, this balance is lost. The magnetic field required for the motor operation collapse, leading to the immediate loss of motor function. The imbalance erratic behavior of the remaining magnetic fields could cause irregularities and instability in motor operation if it does not fall outright. The short circuit will be place a massive load on the power supply or a battery system. If the system is not equipped with the fast acting protective device, the power supply could suffer the damage due to the overload. This can manifest as a triple circuit breaker, blown fuses, or permanent damage to the power electronics such as the motor controller or inverter in EV. The rapid flow of excessive current through the stator winding generate sufficient heat due to the juice heat I raised to power R losses gives low resistance of the winding. The heat generated can be extremely high and it's occur very quickly. The motor cooling system is designed to handle the heat generated during the normal operation, but it would be overwhelmed in the situation. The winding would overheat within seconds, leading to the insulation breakdown, melting of the wire coatings, and possibly combustions of the surrounding material. The initial overheating can be trigger thermal runaway condition. As the temperature rises, the resistance of the windings may increase slightly but not enough to reduce the current sufficiently. This leads to even more heat generation, further acceleration to the damage. The thermal runaway could result in the complete melting of the winding and adjacent component. The motor ability to produce torque is entirely depend on the interaction between the magnetic field generated by the stator and rotor. With the winding shorted, this interaction ceases and the rotor loses its driving force. This leads to the immediate stop in the motor output, which can cause the mechanical stress on drivetrain, especially if the motor was under load. In application where the motor is driving load like in EV, the sudden loss of the torque can lead to the jerky or abrupt deceleration, which could cause the further mechanical stress or even damage to the drivetrain components. The rotor, which is still spinning due to the inertia, will not receive the proper magnetic force to keep its center and balance. This could lead to the rotor wobble or misalign, placing additional stress on bearing. If the bearing are stressed beyond the limiting, they could fail, causing the further mechanical damage to the motor. The losses of the magnetic balance might cause the motor to produce abnormal vibration and noise. These mechanical disturbance could lead to losing the motor mount or damage the connected mechanical systems.